Continuation of strength of materials. We are still on stress, and this is another example we are going to tackle. Let's go to the question. Now, the question is asking us to find the average shear stress in the pins at A and C. So we have one pin here, which we have here, and we have another pin here. This is the free body diagram. As I said, for you to be able to solve this question on stresses very easily, you need to provide your free body diagram. And also, your free body diagram also carries marks. It depends on your lecturer. So let's go to the question. The beam shown is supported by a pin at C. Now, whenever you hear pin has two reaction forces, the X forces and the Y forces. So we here at C, for the free body diagram, we can see that we have CX and CY. Those are the two forces acting at a pin by a short length AB. So this is the short length AB. Now, if W, so they gave us W, so let's write here, let's indicate. If W is 30 kilonewton per meter, and determine the average shear stress in the pins at A and C. Each pin has a diameter of 25 millimeters. Assuming L is 1.8, so L is 1.8 meters, and theta here is 35 degrees. So what the question is asking us to do is we should find the average shear force, or average, we should find the average shear stress. Now, how do you go about that? So in this case, what you must do is that we are going to use, at equilibrium condition, we need to find the reaction forces. All right. So for the reaction forces, let's see. For the reaction forces at equilibrium, so we are assuming that the beam is at equilibrium. The sum of moment, so we are creating a moment at C, should be equal to 0, because that's where we have a lot of reaction force at. So let's generate that. So with that, that means that we are going to have, let's create a moment. Now before then, we need to resolve these forces, right? For these forces, we have a force coming here, which is Fy, and we have another force coming here, Fx. So we have a force that has been resolved to get F1 in the rod 1, right? Yes. So for that, let's try to, we are creating a moment at C. So first, we know that from here, this is going to move clockwise to C, and I'm taking my anti-clockwise to be positive. So since it's moving in clockwise, it's negative. So you're going to get negative F1 sine theta. And in this case, theta was given to us as what? 35, right? So theta was given to us as 35. So to be sine 35 degrees. Then the distance it covers is 1.8 meters. 1.8. Now, then we move on to the next one. Now we can see this W is also acting as a center of the beam. So we need to also resolve the find the moment from the W to the C. So in this case, how do you do it? Now they gave us this, the unit of C is 30 kilonewton per meter, and we need to find the force here using the total distance. So for that matter, we are going to note that when we multiply, let's do some arithmetic here. When you multiply kilonewton per meter by meter, this will cancel out. We are going to have our force, right? Which is kilonewton. So in that case, what you are going to do here is that we are going to have 30 kilonewton per meter, then times n times 1.8 meters. That is the force that we are going to get, because when you multiply 30 by 1.8 meters, that's 30 kilonewton per meter by 1.8 meters. You're going to have the force, which will be in kilonewton. Then the distance here, the W is acting at the center of the beam. So that means that we're going to have 1.8 divided by 2 meters, which is equal to 0. I hope you got that. So from that, when you do correctly, we are going to establish that our F1 will be equal to 47.0731 kilonewton. That is our force in F1. Then we continue with the reaction forces. So we are going to find at equilibrium the sum of forces. So the sum of forces in X component should be equal to 0. So in that case, we are going to resolve this. So we have our Cx, which is moving in the positive direction. So Cx. Then we have our Fx, which is moving in the negative direction. And we now have our F1. Note that Fy, let me establish something here. Fy is the same as F1 sine theta. And Fx is the same as F1 cos theta. So don't be confused. So with that, we are going to have our brackets in a way that we are going to get 47.0731 kilonewton. Then multiplying cos the angle of 35 degrees, which will be equal to 0. So in that case, we are going to have our Cx. Our Cx is going to give us 38.5600 kilonewton, because we resolve it in what? The X component. Now let's continue. For us to find Cy, we need to create a moment at B so we can get our Cy. So creating a moment at C, we are going to use the equilibrium condition that the sum of moments at B should be equal to what? 0. So the sum of moment at B should be equal to 0. So in that case, we are going to have our Cy here will move in the anti-clockwise direction to B. So we have our Cy. Then the distance is 1.8 meters. Then minus, we know that when we resolve the forces, right? When we resolve the forces for our W, right? For W, I established that with W, when you multiply 30 by what? 1.8, that is 30 kilonewton by 1.8 meters, you're going to have the force. And the distance, so we are moving from this side. The distance it's moved to B will be what? 1.8 meters divided by 2. And we equate that to 0. I hope you understood that, because this represents the force. We need to find the force from the W, because when you multiply, it's kilonewton per meter. As I established, when you multiply kilonewton per meter by meter, you're going to have the force. So this is going to represent the force multiplied by the distance. So when you do that correctly, you're going to get our Cy to be equal to 27.000 kilonewton. So now we try finding the resultant force for our C. So finding the resultant force at C bar, we are going to have that it will be the square root of the CY, which was 38.56 kilonewton squared plus 27.00 squared. And in that case, when you do that correctly, you are going to have our resultant force to be 47.0731 kilonewton. So as far as we found the reaction forces, then we move on to the question. With question number 1, when you go to the question, we are asked to find the shear stress in both pin 1, pin A and pin C. So for us to find the shear forces, so let's write finding the shear stress in pin A. So with that, we know that the cross-sectional area of pin A, both pins have a diameter of 25 millimeters, right? So in that case, we try finding the area. So we finding the area, we know that area of pin A will give you pi on 4 multiplying by what? The diameter, which is 25 millimeters squared. You are going to get 490.8739 millimeters squared. Then you come that since we found F1 will represent the resultant force at pin A, right? So therefore, you finding the shear stress as what? Pin A will be equal to the resultant force, which was F1 over the area of what? Pin A. In that case, we know that the resultant force that we had was 47.0731 kilonewton all over the area, which was we had 490.873 millimeters squared. So for us to get it in megapascal, we change this to what? Newton. Are you getting it? So when you do that, you are going to multiply by 10 exponent 3. And when you do that correctly, you are going to get 95.9 megapascal. Now let's move on to B. For B, we are supposed to find the average shear of what? Stress. And we should note that for the diagram given, A at pin A is a single pin. So this is a single pin, but this is a double pin. Let's note that. So that therefore, when you are finding the area, you are going to multiply it by 2 when it is a double pin. So we're finding the average shear stress in pin C. So let's find the shear stress in pin C. What you need to do is that we also find the cross-sectional area, which was already found because they all have the same diameter. So with C, when we resolve the C, we had that our answer was for the reaction force at C, our answer was 47.0731 kilonewton. So in that case, when you are finding that the shear, this one at C, you're going to have it to be 47.0731 all over. Since the double, note that C is a double what? Shear, right? It's a double shear connection. So in that case, it will be 2 times the area that we had, which is 190.873 millimeters squared. So in that case, when you do that correctly, you're going to have it to be 47.9 megapascal. That is it. 47.9 megapascal. Yes, that's very simple.